Pretty much everyone's here. We're good to go. All right, cool. So today we have Ryan visiting us from Caltech. He did his PhD at McMaster's and then his first postdoc at Kentucky at Fermilab. Now he's a postdoc at Caltech. Today he's going to tell us about effective theory of Coulomb current.
Okay, cool. Thank you. So I guess I need to hit play, which I thought I had done. My mouse. Okay, cool. Okay, so thank you for having me. So today I'm going to tell you about something that's probably a little unfamiliar. So I'm going to talk about nuclear beta decay. So two of these works just appeared this fall. There's another paper that's coming out soon about the iconal algebra that I'll tell you about. And then there's a fourth paper where we're trying to write up the calculation we did of the three-loop contribution to the anomalous dimension for this process. Why should you care about this? So that's the most important question. So presumably you care about fundamental physics, and you might not be particularly interested in the details of nuclear beta decay. And so the pitch is really simple. It's just that there's a lot of experiments that do probe fundamental physics that rely on large nuclear targets. So for certain things, you're just stuck with dealing with heavy complex nuclei. And when that happens, if they have a large charge and you care about weird pockets of phase space or you have precision goals, then you need to worry about Coulomb corrections. So the fact that the nucleus is a big charge changes power counting, and you can get corrections that are enhanced by the charge of the nucleus. And so zooming out a little more from a broader perspective is important when you want to do precision physics. It's important when you worry about pieces of exotic phase space or you worry about reactions near threshold. But I think what I would say is more generally, this is a foundational theory in some sense. So these are results in QED. So if you learn something new about QED, it's it should be your favorite field theory, I hope. And it's an important thing to learn about. Okay, so the talk is going to be organized like this. I'm going to tell you about effective field theory and beta decay. Feel free to ask questions whenever you want. So the first talk is basically going to be a sketch and motivations. The second part is going to introduce the effective field theory that's used. It's an extremely simple theory, so I'll actually be able to fit a Lagrangian on one slide and walk you through everything. I'm going to then discuss some iconal algebra, so kind of like YFS iconal algebra that you can use to simplify the problem. So reducing kind of a factorial reduction in the number of diagrams you need to evaluate. And then I'm going to talk about some gauge invariant subclasses. And then the third part, I'll get to some pheno, where I make contact with something that's called the Fermi function. So if you're unfamiliar with that, I'll introduce what that is and how to connect that to a kind of more modern or standard MS bar quantum field theory object. Okay. So why do you care about superallowed beta decay specifically? So this is actually the most precise extraction of VUD, so the CKM matrix element. So you might be surprised because it's a big messy nucleus. So you might think, how could you ever do any precision physics with this? And basically, there are certain symmetries that are helping you. So there's a conserved vector current, and there's an isospin symmetry. And so at a level of, let's say, 1%, everything reduces down to a Clebsch-Gordon coefficient. And so you're kind of safe up to like let's say 1% accuracy without having to worry or think too hard about hadronic physics. Okay, that's kind of the starting ground of why this is not a bad idea. Most importantly, yeah. That's right. Yeah. So it's very crucial. So so specifically that you talk about superallowed decays. So this is 0 plus to 0 plus. And that guarantees that only the vector current is going to contribute. At least at kind of like leading order and all this stuff. Okay, so there's some sausage making that goes into this plot, and I won't tell you about how the sausage is made today. However, just to give you an idea of at least what the community expects in terms of precision, the extraction of EUD is at 600 parts per million. That's what's claimed in this Hardy and Towner paper. The error budget is plotted on the right here. And the part that I'm going to talk about is this piece, right, which is down at kind of 100 part per million precision, so 10 to the negative 4. This is an extremely stringent requirement, especially as you'll see when you start getting these enhancements from the charge of the nucleus. Okay, and maybe you've heard about this. So there's currently a 2 to 3 sigma tension in CKM, first row CKM unitarity. And so resolving this tension means digging into the theory of superallowed beta decays, because these are the most precise input for VUD. You might wonder why you really need to measure at such like an extreme level of accuracy. And it basically just comes down to the fact that VUD is approximately 1. And so it has a much more stringent error requirement or precision requirement. Yeah. That's a good question, because it's a typo. Yeah. It's everywhere. Yeah. It's a very dumb typo. Yeah. Okay. So the basic point of this talk is that these approximate symmetries that I mentioned, they only go so far. Okay. So at some point, as you push for harder, you push for more and more stringent precision, eventually you need to deal with these kind of 5 bullet points. So the one I'm going to talk about is the one at the bottom, and it's the fact that QED loops eventually modify how you interpret your extraction. So even if you know you basically, what you're measuring when you measure a nuclear beta decay, you're measuring some low energy Wilson coefficient, if you'd like, that's controlling that nuclear decay, even if you can compute all the loops in the low energy theory. And those that Wilson coefficient can, for instance, receive corrections from short distance physics from QED loops. And then additionally, you need to be able to actually have an expression where you capture the long distance QED loops. Okay. And so in this talk, I'm going to be talking about radiative corrections that are enhanced by the charge of the nucleus. Okay. So the historical approach to this is to basically assume some kind of factorized form, and you shuffle terms into different places that are by and large determined by some kind of historical convention. Okay, so for instance, the leading Z resummation of all the Coulomb corrections is handled with something called the Fermi function, and that's packaged into something called a lowercase ft value. Okay, this is done using a Dirac wave function. The radiative corrections are assumed to factorize from the Fermi function. Okay, so you just write it like this. There's no, this is best thought of as an ansatz. Okay, so you hope that by writing it in a factorized form, you reduce kind of, or you make the perturbative series for that 1 plus delta R prime, it converges faster. It has better convergence properties. Okay, so there are natural questions again, and then often these radiative corrections are really computed in models. Okay, so you can also ask if things end up being model dependent. Okay, so at the level of precision that's required here, all of these questions are kind of concerning. And so the questions I want to ask and answer in this talk are, okay, so this Fermi function is supposed to resum all the leading Z stuff, so that should be a big class of diagrams. So really precisely, what are you doing? And how is that related to what you would compute if you just sat down and did fixed order perturbative or perturbation theory calculations? Because if you want to compute subleading orders in alpha, that's what you're going to do. You're going to do fixed order calculations. Yeah. Good. So this is, yeah, so this is so once again, this is, if you like, a convention, but delta is nuclear structure dependent corrections. So delta R prime should depend on just the point-like properties of the nucleus, and delta NS might depend on, for instance, the nuclear radius. Delta C is an isospin correction, but it is Coulomb in the sense there's a reason why they put a C. The inter-Coulomb forces in a nucleus violate isospin. So this is about half of the isospin violation in superallowed beta decays comes from explicit quark masses. And half of it comes from the fact that the protons, when I add a proton to a nucleus that has a lot of protons, it behaves differently than if I add a neutron. And so I won't really get into those parts of the talk. I would say that's like future work or trying to understand how to interface what we've done with isospin breaking. So there's a subtle issue of like the Coulomb field is generating some of these external corrections, delta r prime, but there's some internal piece, internal to the dynamics of the nucleus that you need to handle.
And then just like a regular resummed factor 2 pi alpha where the ball still electron where
So that would be the Fermi function. Yeah, and then you can just find that by computing graphs. Yeah, so I'll explain how that fits in the third part of the talk. Right, so it's just so it's kind of like a half-life, but the Fermi function is f, so it's like a half-life that you've kind of integrated the Fermi function over all the phase space. So there's some conventional normalization factor that relates the half-life of the beta decay to the expression involving VUD. And so
FT is just a variable instead of just one variable.
yeah, that's right. It's just one variable. You measure, yeah. So it conceptually or like in terms of matching the precise observable to what you're computing, it's actually a very easy experiment. You put a bunch of nuclei on a tape or something, and you count how active they are. You count.
It's a gamma decay.
Yeah.
Historically, expressed. Right, so there is like a phase space that
Phase space factor.
And the coupling.
That's right.
G-firm squared everywhere. You strip it off. Right?
That's right. That's right. So you should just think of it like the overall decay rate goes like VUD squared times something. That something is if you were to work at like 0th order and alpha and 0th order and everything else, it's easy to compute. In this case, not 0th order and alpha because you sum all the Z alphas, and that would be FT. And then they're just saying, oh, the real answer is slightly different. So I write down these correction factors. And then it's a little odd. There's another correction factor down here, and these are called the interradiative corrections. And then you also should worry, certain questions you should also ask now are like, are you double counting, for instance? So you have short distance radiative corrections, you have these long distance ones, and are you being extremely scrupulous in making sure that you're never double counting?
Trying to go back to one slide. Right?
Yeah.
You circle this affinity that's the focus of your talk. Naively, you think this one is the largest compared to the other one.
Yeah, it's by far the most well, what do I want to say? I think I'll show you in a slide what you require. It's certainly a hard part of the problem. So
I understand it's hard, but just want to understand.
No, it's a big effect. Like it enters. This isn't some esoteric thing where it hasn't been included in fits, and it's going to be like a 10 to the -6 effect. You need, yeah, just 2 slides, and then I think I'll have a rough answer to your question.
The experiments measure most of the lifetime, right? So
yeah, totally inclusive. That's correct. That's correct. Yeah, you should be totally inclusive. So, yeah, that's right. Okay, so so the basic idea of this is that you're going to have loop diagrams like this, and in regions where the photon wavelength is long compared to the nucleus, you're going to see the entire nuclear charge. So you're going to get enhancements that are proportional to Z. Okay, and so Jen, hopefully this answers your question. So this is kind of the power counting that I'm going to advocate in this talk. So you're mostly dealing with nuclei with Z ranging from like 6 to 30. Okay, that's what enters the fit for superallowed beta decays. So let's count Z like 10, and you're going to get logs that show up that are order like 5 or 6, something like that. So that's something like ME over mass of proton, sometimes mass of electron times nuclear radius, sometimes that log squared. So let's count logs also as order 10. And then this is conservative, right? And then I'm going to ignore factors of 1 over pi to the n. And there's a good reason for this, because sometimes they're just not there. Like Maxine mentioned, the Sommerfeld factor goes like pi alpha, not alpha over pi. Okay, so you when there's Coulomb physics involved, you should be wary of factors of pi. And if you just go through and demand alpha to the 3/2 precision, which would correspond in this power counting to 10 to the -3, which is right, still an order of magnitude above the level of precision that would be required. You end up finding that you need terms, right? Some of these are clearly logarithmically enhanced, and you should be able to get them if you know what to do with renormalization group, but you need like 6 loop results. Okay, and you need genuine three loop input. So as you saw from that plot, there was an error associated with delta r prime, and I would claim in that plot that error, based on how they did it, is wildly, it's too aggressive. But yeah, so these effects are in fact important. Okay, so yeah.
I use 1 in 60. I only do my alpha because we have our.
So you do 6 z's and 3 logs is 9 powers, so 9 halves times, so it's 6 minus 9 halves. Yeah. Okay, so so there's a lot of scales that go into this, okay, and that makes life hard. But you can take advantage of ideas from effective field theory to minimize your theoretical error. Okay, so the kind of scales that you would find that would show up here are like the W mass, the nucleon mass, the mass of the nucleus itself, Fermi momentum, nuclear radius, lepton energy. Okay, and the way you should approach this is to do 1 scale at a time. Okay, so there's going to be, I'm not going to talk about this whole sequence of effective field theories. I'm just going to talk about the lowest energy effective theory. But you should imagine a sequence of effective field theories, and that the matrix element will factorize at leading power. So up to power correction, something like PR, okay? The matrix element will factorize in this way, where these you can identify as Wilson coefficients in the low energy theory. Okay, and so what I'm really going to be talking about is like kind of the all orders in alpha and Z alpha structure at leading power of this matrix element. Okay, so that's equivalent to doing the matching, getting the Wilson coefficient in this lowest energy effective theory, and studying high perturbative orders in this low energy effective theory. Okay, so what you're really doing is you're kind of untangling this ball of yarn. There's all these scales, they're overlapping, and if you try and analyze things in this mess, life will be hard, but if you can pull it apart into individual pieces, life is much easier. Okay, even if you have to do 5 calculations, they're 5 tractable calculations instead of 1 giant mess. Okay, so the basic philosophy will be 1 scale at a time, to always use physically propagating degrees of freedom. So I include this specifically because this is in contrast to how nuclear beta decays have been handled historically. Often people do this model where you have something like a neutron decaying to a proton and an electron, and then you imagine that you have a background Coulomb field. Okay, and these things are treated as relativistic, and obviously you can start asking questions of, I don't have neutrons and protons in my lab, so why are we including these non-propagating degrees of freedom? So a consistent expansion in small ratios of scales and whatever small couplings you have in your theory. And then they should be giving you some systematically improvable object that you can interpret within quantum field theory and can therefore make use of things like renormalization group technology. Okay, so I think I'm doing okay on time. So now I'm going to talk about this part 2. So I'm going to introduce what the effective field theory is, the kinds of graphs that we're going to be interested in, and then I'm going to talk about these iconal identities and how you can identify a new class of gauge invariant, new gauge invariant subclasses within this problem. Okay, so point like EFT of nuclei is really just a heavy particle effective theory. So this is HQET if you're familiar with HQET, or NRQED if you're familiar with NRQED. Okay, so some recent work has applied this to other exciting topics like black holes and heavy dark matter. But for the level of this talk, this is just like the most rudimentary application of this this stuff. So we're working at leading power. So basically all that's going on is that when a particle becomes extremely heavy and on shell, if you were to expand its propagator, you would find that as the momentum kind of is much, much smaller than the mass, the propagator has the simple form where it just looks like 1 over v dot k. So there's only one pole. Okay, so it looks like, if you'd like, you can say you've integrated out the antiparticle. And there's equivalent to treating this as a classical kind of static source. Okay. It just moves along some trajectory that you specify with a forward velocity. This also has heavy particle effective theories also make manifest that couplings are spin independent. So what that means is that the kinetic term looks like V dot D. And so you don't have gamma matrices. So you don't have spin structure in your coupling to photons. Okay, so that also simplifies the problem. Okay, and that's all you really need to know. So this is the Lagrangian. So this is what you're starting from. And it's fairly straightforward. So you have a nucleus A, which is described by some heavy field. That nucleus has a charge ZA. You have a nucleus B, also a heavy field. We're going to work in the static limit. So that means when the nucleus, the momentum transfer to it is so negligible that you can treat both the four velocities as equal. They're both at rest. We have a dynamical photon field. We have QED for electrons. We have a neutrino. And we just have some external operator, okay, which is just a weak current. Okay, so now I'm going to describe in this part of the talk how you can take advantage of iconal identities that emerge in that show up when you do these heavy particle field theories to simplify all the loop calculations you have to do. Okay, so it's well known, although I don't think it's actually that well known, that the sum of all cross ladder graphs reproduce a Dirac field. So I think it's better known that the sum of ladder graphs and the non-relativistic limit give you the Schrodinger equation. But if you'd like to reproduce the Dirac equation, so if I take this particle as light and this one is heavy, and I take this thing's mass to infinity, and I don't make a non-relativistic approximation for this particle, I need to keep all cross ladder graphs to reproduce the Dirac equation. Okay, so this is some very old results where people basically did mu on electron scattering. And then the discussion in Weinberg is nice in that it explains that this is a actually universal result for any composite particle that's heavy. Okay, so you can derive this. There's a set of crossed ladder identities, and I'll kind of try and give you some intuition.
Wait,
Yeah.
You're assuming ZA equals ZB?
Yeah, so that's a good point. Right. So that is what's assumed here. Yeah, to derive this.
So physically, like A is going to be the particle before it's beta decay.
And they have different charges, which is a problem. And so that's yeah. So that's the new part of these iconal identities. So so that's the paper that will come out later this year. But basically, that's a nice story for how a Coulomb field emerges if you just have a static object move through your diagram. But for any charged current reaction, that's not sufficient, especially when I want to do these subleading orders in alpha. Okay, so I'll try and explain how to generalize this for charged current processes. Okay, to give you some intuition, maybe you've seen YFS algebra. So you like read about soft photon identities, or if you looked at treatment of IR divergences in Peskin and Schroeder, you'll have seen something like this, where you have emission off of a photon, off of an electron line by two photons, and the sum on the right or on the left looks very complicated, and it turns out when you add it all together, you sum over all the permutations, you actually get a much simpler result of uncorrelated emission. Okay, so there's a similar identity where you have, in one of these heavy particle diagrams, a photon coupling to a particle in the initial state, interfering with a diagram where the photon couples to the particle in the final state. And naively, right, if I cover these, this gives 0. But because of these causal regulators, you get a pinch. So you get a delta function. Okay, so this ends up setting the energy transfer through that photon to 0, and it acts just like a Coulomb mode. And so the generalization of this to an arbitrary number of particles is what gives you these Coulomb identities. So you would add up a bunch of diagrams like this. So this is for 2 photons. So there's 6 diagrams. So there's 2 plus 1 factorial number of diagrams, and that's in part because I've included this external current here. Okay. And if you add it all up, it turns out, you have, if you'd like, you can count these as ZA, ZB, and ZB squared, right? So you can call this A, B, and C, and they have different powers. But if you add up A plus B plus C, you get the standard identity that's written on the top. So where you have the energy transfer through the first mode and the energy transfer through the second mode are pinched to 0. However, it's clear from looking at this that these subleading terms, right? If ZB is slightly different than ZA, then these subleading terms, I guess there's a missing factor of Z here, they're not gonna give you the same thing as A plus B plus C. Okay, so then the question is, can you do anything with this? Can you get some identity that you can use at subleading orders in alpha? Okay, and so this is important not just for this problem, but for kind of any neutrino physics application. Okay, so the reason why this is important is that you want to simplify the analysis. And so to give you some idea, like at one loop, there's only 3 diagrams you would need to compute in this for this three particle vertex. But at 2 loops, there's 23 diagrams, and at 3 loops, there's like hundreds plus diagrams. So I think I've counted before, and it's like 144 or something. Okay, so this is a lot, and it would basically make these high loop order calculations prohibitive. And I told you that to do the analysis that I pointed out in those early slides, where I said you might need up to 6 loop order, you need genuine 3 loop input. So you need the anomalous dimension computed at 3 loops if you wanted to use our G to get all the terms that I listed on that slide. So we want to simplify what we need to do at 3 loops.
Is there a reason you don't draw a neutrino on?
Yeah, because it's electrically neutral. Yeah. So just to not clutter the diagram. It won't do anything in a.
Oh, okay.
So it's kind of like in yeah, so like
Oh,
it yeah. So this is a common thing if you do like a B decay, often you'll just draw this. And you won't draw the leptons because they're neutral under QCD.
okay.
So these are all the charged particles under QED.
Okay, this is because you're only interested in QED current.
Yeah, and I don't want an extra line going through my diagram that my photons have to jump over when it's just for clutter reasons. Yeah. Okay, so here's the basic strategy. So a sketch, if you like. So the idea is you focus on ladder graphs. Okay. And then you organize diagrams by how many photons are on the right and how many photons are on the left of the current. Okay. So then what you're going to do is you're just going to expand out factors of ZA and ZB. You're going to write ZB in terms of ZA and just expand things out using like the binomial expansion. You know, it's ZB to the n. So you expand that out in terms of capital Z and whatever the residual charge is. Okay, you just do some algebra. You replace the resultant binomial coefficients that you get from just expanding the polynomials by some dummy sum over some index. You can always do that. You can just sum over 1 to get a number. And then you just do some manipulations with the sums, and you find that you get a sum over permutations of lower order neutral current iconal identities, plus emission off of a particle with residual charge. Okay. So what this looks like diagrammatically is you sum over all of this, and you find at leading order, and let's say ZB, you get 2 Coulomb fields. Okay, that's what you must get because it's the leading Z resummation. At subleading order, you get a Feynman rule where you interact with a background Coulomb field, and then you emit a photon off of a particle of charge lowercase z, so like a residual charge particle. And then at the lowest order, you just get 2 photons connected to residual charge particles.
So in reality, it's small z than the plasma.
That's right. Yeah. In reality, yeah, you can just set little z to 1 here. And in fact, on the next slide, so in words, okay, 2 coulombs, a coulomb and an iconal, and 2 iconals. Okay. So for the mathier people who would rather see like a real formula of what this looks like, this is a statement. So I have some matrix element between a state A with 4 velocity V going to a state B with 4 velocity V. I've written like time ordered product Fourier transformed in this shorthand notation. Okay. And then that thing is gonna, all of the Lorentz structure will just be these 4 vectors V mu. They'll just come out. And there'll be this function, scalar function, g of q1 to qn. And then the iconal identity is telling you that this scalar function can be expanded in a simple form, where it looks like a bunch of delta functions, and then delta functions mixed with emission off of a particle of residual charge Z. So this is cool because this is exactly this model that I was complaining about earlier, okay, where you didn't have physically propagating degrees of freedom. This happens only in the heavy particle limit. So I need to, strictly speaking, replace this particle by some heavy particle A with charge little z, or z equals 1. And I have to take a heavy particle B with charge z equals 0. And importantly, you might have thought, if I told you this diagram happens in a background field, that Coulomb field would talk to this particle and this particle. However, the ladder graphs are only communicating from in the original diagram from the heavy particles to the electron. So only the electron is charged under the background field. Okay. So so the main summary of this part of the talk is that there's a successful generalization of these iconal identities for charged currents. This is great because it lets you reduce the number of diagrams you have to compute by a factorial amount. So it reduces that 144 diagrams, for instance, to like 10.
But it also kind of visualizes the leading order Z dependence.
Yeah, the leading order Z dependence. So I'll talk about that. So it's yeah, well, yes-ish. There's also a story there, but that's right. So then you can see, it's going to reduce to diagrams where you just have a background Coulomb field. And so then we can ask questions about what is the Fermi function entirely in terms of a background Coulomb field. Okay. And so I just have one slide on this. I don't think I really have time to go into a lot of detail, but I just want to sketch the idea. So you can use this iconal algebra to relate ladder graphs to a background field model like I was describing. And then you can look at that background. So actually, let me take a step back. So often it's nice to find gauge invariant subclasses of diagrams, because if you can find a gauge invariant subclass, you can evaluate it in whatever gauge you like. And that means while you do a calculation, you might get to use 2 or 3 different gauges in different parts of your calculation, each of which might have its own advantages. Okay, so anytime you can grab a new way to classify gauge invariant subclasses, it's great. So one simple way is to just count powers of capital Z, right? Every power of the large nuclear charge, each power of that Z needs to be separately gauge invariant. So this is different than that. Okay. So here what we're going to do is we're going to analyze ladder graphs, and then at any fixed order in Z and alpha, we're going to take those graphs and we're going to reorganize them in a particular way. So since I know how to take all the ladder graphs and relate them to this background field model, I'm just going to rewrite my my amplitude at that order in perturbation theory as the same amplitude in the background field model, and then everything else. And because I know how these ladder graphs resum to give me all these different terms in the background fields, Lagrangian, this is relatively straightforward. So since the background field model is gauge invariant, I now have a second class of diagrams, the ones in the background field, which are gauge invariant by construction. And since the entire amplitude at every order in Z is gauge invariant, then that means that my second class, the complement of class 1, has to also be gauge invariant. And then it turns out that the diagrams that fall in this class, you can vanish diagram by diagram in Coulomb gauge. And so by doing this, you can basically eliminate something like 70% of the diagrams you would have to compute. And you kind of end up with this much simpler set of Feynman rules for computing these graphs. Okay.
Just to be sure, so
yeah.
It vanishes in Coulomb gauge, it also vanishes in other gauges, right?
The whole, so the whole subclass vanishes in any gauge because it's gauge invariant.
It's just in Coulomb gauge.
It's diagram by diagram in Coulomb gauge. Okay. You can just compute any of them. Yeah.
In other cases, maybe you have to sum over.
That's right. You'd have to sum over all of them, and the integrals are hard, and it would be difficult to see. Yeah. Okay. So now in the last part of my talk. Please give me 10 minutes left warning. But Let me now talk about this Fermi function question that you asked about, Maxime. So how do you do the leading Z resummation? So indeed, it trivializes, and you can think of it like a background field. So for the uninitiated, what is the Fermi function? So historically, the way that Coulomb graphs were resummed is you said that you should just evaluate the wave function of the electron at the origin. But the electron is relativistic in beta decays. So you can't use a Schrodinger wave function. You have to use a Dirac wave function. And unfortunately, that Dirac wave function diverges at the origin. Okay. So this has certain pros. It manifests, and what people did historically is they would just chop this off at the nuclear radius. Okay, so another thing you could do is put in explicit UV physics, like specific charge distribution for the nuclear radius. But I'm just going to ask what in the effective field theory, where everything is point-like, right, where I want to manifest universality in the point-like limits, what is the right thing to do? So this has certain advantages. This prescription, I never mentioned the microphysics of the nucleus. So it manifests the long distance Coulomb stuff. And it resums a series to all orders in Z alpha. But it's regulator dependent because it was written down in like the 1930s. So there's no renormalization here. You just stick in a regulator, and then it explicitly shows up in expressions.
So in physical essays, this usually gives a logarithm of the charge radius.
That's correct. Yeah, that's correct.
So, but the corrections on top of this log would be sensitive, right? So you're trying to, let me ask you, you're trying to fix the coefficient in front of this log, or all other terms that come from my
all terms, not just the coefficient of the log, not just like leading log accuracy.
Well, if I would change the charge distribution, the corrections would they know?
Yes. So there's in our language. So you would do I have? I think I have slides that sketch this. So basically, those would get absorbed into a Wilson coefficient. But there's still a question of what is the matrix element in the low energy point like theory. Yeah, but if you change the microphysics, it's going to get shuffled into a Wilson coefficient. And then there'll be other things that will get shuffled into power corrections, which would be like the Wilson coefficient of a higher derivative operator. Okay. So I think a lot of particle physicists, if you showed them this problem, they would just maybe say, why don't you just calculate something? So just compute. Like, it's not that hard. Like, you have a Lagrangian. You should at least compute it first order. First order is easy. You get the Z alpha over pi, or pi Z alpha over beta. Second order, it looks like this. Okay, so this was, I don't know. For me, it was a little hard. So it took some time. You need some integration by part set entities, but it's relatively straightforward. There's one graph to compute. But this is the closed form expression for the renormalized amplitude in the effective theory. And then you might have hoped that you could like compare this to the Fermi function and pick off kind of just figure out an ansatz for what the resummed MS bar expression would look like. But I hope you just look at this for a little while and can convince yourself that there's no obvious pattern. And there's also a problem that there's in DimReg, there's IR divergences that show up in these graphs and UV divergences. And it's very hard to pick apart what's going on here. Okay, so just as an aside, let me discuss this factorization of amplitudes, and this should come back to your question, Maxine. So the idea is that in this effective field theory, I have a Wilson coefficient and an operator. And the Wilson coefficient is capturing short distance matrix elements, and the long distance matrix elements are explicitly computed in the EFT. Okay, so you can just do this explicitly using method of regions. So you take a loop integral like the thing I wrote above, and you have a short distance region where you do one Taylor expansion and a long distance region where you do another Taylor expansion. And the sum of those two things will give you the original integral. Okay, and what's really going on, there's a structure, which is that there's going to be this factorization. And the fact that it's a sum is just from taking 1 times that alpha and that 1 times that alpha. That's why at one loop it looks like a sum. But more generally, this is like a multiplicatively factorized structure, and this will work to all orders in perturbation theory up to power corrections, which in this example are controlled by this small ratio of masses. So what if I just stuck in a form factor? So here, f of q squared over lambda squared is your charge distribution of the nucleus. And I analyze a graph with a background Coulomb potential. So I'm going to stick in a photon mass, which is kind of like a Thomas Fermi screening from an atom. So I'm now going to have three scales. I'm going to have a scale set by the momentum of my electron, a scale set by nuclear physics, and a scale set by atomic physics. And the amplitude is going to factorize into this soft, hard, and UV matrix element. Okay. So this scale, P, this is our EFT matrix element, where I don't have a photon mass and I have a point-like nucleus. Okay, so notice that in going from this slide to this slide, the form factor disappeared and the photon mass disappeared. They were just set to 0. Okay, the soft function down here, this is great. We actually know this to all orders in perturbation theory. This is a YFS result, basically. Okay. So what will end up happening is that at leading power, all of the corrections that you would get from, for instance, solving the Dirac equation can be shuffled into this UV matrix element, which is like a Wilson coefficient in our low energy effective theory. So you can take the literature on people solving the Dirac equation and extract what this UV Wilson coefficient is at all orders in Z alpha, but leading order in alpha. But what I'm really going to be talking about is the goal was to understand, the high order structure of this matrix element. That's the goal that we're after. So now the question is, can we have our cake and eat it too? So before I told you you could do a wave function and you could resum all orders in Z alpha, but you live with this, either UV physics dependence baked into the answer or a regulator that's unphysical. Okay. But you get the answer at all orders in alpha. On the other hand, I can do a 2-loop calculation and I can write something down for you, but it's very unclear how I would get higher orders in perturbation theory without just pain on pain on pain. Okay, so the key is to understand what is the Dirac wave function and does it have a perturbative loop expansion? And the answer is, of course it does, because any scattering state can be written with a Lippmann-Schwinger equation. So I can just take the Lippmann-Schwinger representation of scattering states, insert complete sets of eigenstates, and I get something that looks exactly like my one loop integrand, but with this extra factor, which is basically just saying that I translated my operator from the origin. So that's all that's happened. And at arbitrary order in perturbation theory, this factor just picks up the momentum on the innermost leg of the graph, and that's because the operator has been translated in X. That's one way you could interpret this. Okay, so if this thing has this loop expansion, then why don't I just reinterpret this exponential as a kind of form factor, right? I can use method of regions on this too. There's nothing that prevents me from doing that. And therefore, this wave function will have the same factorization formula as my amplitude, but with now a Wilson coefficient that is regulator dependent and depends on X. So these two are the same. The UV physics has changed, so the Wilson coefficient has changed. Okay. So what's kind of remarkable is that those graphs can be computed at arbitrary order in perturbation theory. Okay. And they can be actually, even before you renormalize them, they can be resummed into an analytic expression that depends on Bessel functions. And an all orders result can be obtained for this UV region that depends on X. And so now I have a wave function, I have a soft function, and I have a short distance function, all of which are known to all orders in Z alpha. And so I can just extract the all orders expression for the hard matrix element, and it's given by this. And this reproduces the answer at 2 loops, like bang on. We did this for the non-relativistic problem. It reproduces things at 3 loops. So the answer is yes, you can. And so now, if you'd like, this is a translation between a finite distance cutoff regulator scheme and MS bar. That's effectively what we've done. But it's important because if you want to do subleading orders in alpha, you need to be able to interface with the regulator scheme you understand. So if you want to do MS bar for radiative corrections, you need the Fermi function in MS bar. So now I have the Fermi function in MS bar. Okay. So that's what I just said. And now we can do RG analysis because we understand what we're doing. This is now an operator or a matrix element, an operator matrix element, and effective field theory, and I know how to evolve those with renormalization group. Okay, so the idea is that you have a Wilson coefficient and a matrix element. Yeah.
Our ancestors, 1930s, they choose a regulator, right?
That's right.
Cutoff scale.
That's right.
In some sense, it's not that wrong because
it's not that wrong.
Yeah, I can view it as they're guessing the Wilson coefficient.
That's correct. That's correct. That's correct. I think that's a fair interpretation.
Right. So then,
and their ancestors put in a UV completion and computed an explicit UV completions and got good answers.
And then what you are doing, did you assume factorization or factorization is automatic? You only verify the result.
That's a good question. So notice that this object, I predict, I compute that, right? I didn't order by order. I got some analytic expression for every order in perturbation theory. I summed the result. You can show it's convergent. So this is a prediction. And it has a very particular Dirac structure like this. And that predicts the Dirac structure. There's an old paper by Tremaine, Jackson, and Wild. And they have a nice expression that relates the Dirac wave function at the origin in terms of some, Dirac bilinears acting on a plane wave spinner. And exactly this comes out. So there are certain properties that are predicted, but to extract MH, I assumed factorization.
Right. You assume factorization, and next you verify that against the other calculation, which matches the other. So I can only say I verified the assumption that they factorized after the other I calculated.
Right. So there's some all orders evidence. I would say getting this because the Dirac wave function comes in a factorized form. So there's this structure, and then there's another Dirac structure that's like 1 plus gamma 0. A coefficient plus another coefficient times gamma 0, and it's factorized. And so the fact that I get this Dirac coefficient correct, and you can show that at all orders in Z alpha, the EFT matrix element will only depend on something plus the only two Dirac bilinears that will show up are the identity and gamma 0. So I would say that's quite a lot of all orders evidence that factorization is holding, but it's true it's not like an airtight, the exact ratio between the coefficients in front of the two terms is not fixed by this argument. And so then there's two loop explicit demonstration.
Right. But build on top of this, you could calculate renormalization RG flows of the pieces.
Yeah.
Are they guaranteed to work, or there's a chance they fail?
I don't know. That's a general question about, I guess, RG resummation.
Because I feel the way you match to this coefficient is in some sense is a leading order matching or tree-level matching. You can improve to the next leading order matching, etc. Can you guarantee they won't mix if I do radiative corrections?
Sorry, what mixing?
Those factorized pieces that you assume certain coefficient on top of each. When I try to RG evolve piece by piece, that's what you are going to do, I assume.
Yeah, that's what I'm gonna do. I would say like I would say it's guaranteed, but gun to my head, like, do I have a mathematical proof? No, I don't think I have mathematical proof. But I think that's true of all RG analyses. Yeah.
Because this problem obviously have field scales not too far separated from each other.
Not too far separated from one another. That's right. Yeah. Okay. So for those not familiar, basically RG evolution here, it's rather simple because there's no operator mixing. So you just have to compute the integral of the anomalous dimension divided by the beta function. And this gives you how, Wilson coefficient at one scale is related to a Wilson coefficient at another scale. And then what you can do is you can evaluate this thing at some scale where there's no large logs. Okay, and then you can evaluate this thing at a scale where there's no large logs. And then you can express this thing as this thing times the ratio of this thing divided by basically that expression I had in the last slide, this exponentiated anomalous dimension over a beta function. So this is kind of standard RG stuff in, I don't know, flavor physics or other traditional arenas of effective field theory. Okay, so now I'm going to tell you something else that's neat. So it turns out in this effective theory, there's new symmetries. So we wanted this anomalous dimension, and we specifically wanted this coefficient in the anomalous dimension. Okay. The leading and Z coefficients, as you pointed out, Maxime, are just fixed by the Dirac equation. Okay. The lowest order terms you can grab from the HQET literature, because that's where there's just a object of charge 1 and an object of charge 0. So those are known up to 3 loops from some Grozen papers. And then we found that you can show that there's a symmetry in the massless limit. So you can extract the anomalous dimension by setting masses to 0. And if you have a massless electron, the theory has an additional symmetry of interchanging kind of the identities of charged particles, kind of taking an electron and turning it into a positron and swapping the 2 nuclei. Okay. And so what that means is that the chart for the anomalous dimension looks something like this. So the stuff in yellow is known from the HQET literature. The stuff in blue is known from the Dirac equation. If you'd like, this box could have been blue, but it's 0, so it's not very interesting. And the orange lines tell us what's related by symmetries. Okay, so if I know something on one side of the orange line, I can predict the other thing that it's connected to. And so with in our short paper, we quote the result for the 3-loop anomalous dimension. The actual write-up of that is kind of under construction. But with this result, actually, the anomalous dimension is known complete through 3 loops, and these 2 terms are known from the symmetry. So it's kind of known to like 3.5 loops. So you can do resummation at very high order, and now the problem kind of reduces to computing the actual operator matrix elements as opposed to their anomalous dimensions. Okay, so you can do a nice thing that you can do with this is you can do different power countings, like counting logs and factors of Z differently, and you can do this all systematically. So you can just write down the most general form of the anomalous dimension, the most general form of the beta decay function. And so for instance, in this power counting, this is the necessary input to order alpha to the 3/2. And we have all the input, so we can make a graph like this, where we compute ratios of Wilson coefficients at different orders in alpha, varying renormalization scales as a function of Z. Okay, and the last thing I want to talk about is a bit of a cute application. So the Sommerfeld enhancement, just it'll be useful to have this here. It looks like 1 plus pi Z alpha over beta. And this story is about this factor of pi. 2 pi? Oh, sorry. Well, it depends. I didn't write what it was equal to. So I can't be able. It's a 2 like this.
Yeah, the Sommerfeld enhancement is 2 pi alpha over velocity.
2 pi alpha over velocity. 1 second. Yeah. So okay, so maybe there's a typo on the next slide, but let me come back to this. Okay, so I was pretty sure I wrote this morning, but for the purposes of what we're saying, order 1 number, I guess, and then I'll check afterwards. But the real question is, why are there factors of pi, which you're not going to fake with factors of 2 or whatever? Because normally what a loop expansion person will tell you is that the expansion is in alpha over pi, or alpha over 4 pi. So we're off by pi squared, right? So naive estimates are off by a factor of a transcendental number that's of order 10. So that's like that's a rough place to be, because then you start worrying about like, am I missing enhancements of order 10 to the n at every order in perturbation theory? It's kind of the concern. Pardon? So that's a good question. So I'll tell you where it's coming from. So why do you think it's coming from the log, out of curiosity? That's right. So that's where one of the pi's comes from. So one of the pi's comes from genuine 3D physics. So you have written it in a suggestive way, so that you have 2 pi I times from a delta function. But basically, if you look at a 3D Euclidean loop integral, the factors of pi are different than a 4D integral. Okay, so that's where one factor of pi comes from. But the other factor of pi comes from an IR divergence. Okay, and indeed, you end up getting some. So it's coming from a log, basically. So there's an old paper by Ahrens, Becker, Neubert, and Yang, where a similar thing happens in Higgs to glue, and they're able to deal with some of these large pi enhancements from what do I want to say? From an RG analysis, but the RG analysis is actually very simple. You basically analytically continue your subtraction point from a space-like to a time-like variable. And so what that does, right, is that this log, which is like negative p squared over mu squared, goes to negative p squared over negative mu squared. And so you don't have a factor of I pi anymore, but that I pi needs to go somewhere. So it goes into the soft function, because these are related by an IR divergence in my hard matrix element and a UV divergence in my soft function. And when you put it in the soft function, that's good, because we know the soft function to all orders in perturbation theory. And then it turns out you can look at the all orders matrix element that I wrote down before. And you can see precisely this exponential that I mentioned appearing. Okay, so good. So conclusions and outlook. So where are we and what have I really done? So the whole talk, I ignored power corrections and isospin breaking, and we haven't done that. Okay, so that's as far as like an EFT framework for these nuclear beta decays goes. I think at leading order in alpha, it's very straightforward what one needs to do. But what we really studied is the leading power isospin symmetric limit, but we've studied it kind of at very high orders in perturbation theory and made some statements that are claims that are supposed to hold to all orders in perturbation theory. We've got some all orders factorization statements, MS bar definition of the Fermi function, and new perturbative input for the calculation of the anomalous dimension. Okay. And so what's next? Right. So this is related to what you asked